You know about exam 1 this week, Thursday. Please arrive at least a few minutes early, because we will have you come forward and pick up answer sheet, information sheet, scratch paper, so that the exam proctors need only to distribute the exam itself. The exam is, unfortunately, strictly multiple choice format. We just haven't the time and wherewithal to deal with any other format during fall and spring. But we'll survive. 24 questions. What is the material for which you will be responsible? Be with us this Wednesday and you'll know. But I expect that the material for which you will be responsible will carry on through indicators and buffers, and anything we manage to get to beyond that. Also, as I said, if you have a legitimate conflict, we want, if possible, for you folks with conflict, like you might have 46 lab Thursday evening, to take the exam earlier in the day on Thursday. Available time slots 2 to 4 p.m. or 4 to 6 p.m. Location, the department conference room, a very nice location. And I need from you a written note if you are in this conflict category, so that I can plan on you being present with us for this earlier in the day arrangement. So we proceed with acid-base equilibrium analysis considerations. And start today by introducing ourselves to an important definition. Percent ionization, which is nothing but a numerical measure of ionization extent. By definition, percent ionization is the equilibrium molarity of a derived species from the ionizing solute. Like for acetic acid solution, the obvious derived species is acetate ion. Divided by the initial molarity, the numerical label you see on the bottle for the ionizing solute itself, multiplied times 100%, since we expressed this as a percent. Example, last time we talked about determining with our general recipe x squared over m sub I minus x, the hydronium ion concentration for 0.10 molar acetic acid. We found the hydronium ion concentration, which of course is the same as the acetate ion concentration, be 1.3 times 10 to the minus 3. So for that solution, percent ionization is 1.3 times 10 to the minus 3 times 100% over the numerical label on the bottle. 1.3%. Now, on what factors does percent ionization depend? We've already considered each of these factors, but have not in an explicit fashion mentioned such in regard to the relationship to percent or extent of ionization, because we did not yet give you this definition until now.
Acid dissociation constant, or the strength of the acid?
Ionization constant, yes. The strength of the acid or the base. So we'll write down Ka, if we're dealing with an ionizing solute, that's an acid, or Kb. Now I told you there are two factors. What's the other factor? No, because if we change temperature, we're going to change Ka values. And now we got a whole other ball game to play. So now we're going to vary temperature. Yes! Solution concentration. Have we not realized that as you add solvent to a solution of a weak acid or weak base, you increase the extent to which the weak acid or weak base reacts with water. Right? So the other factor is solution concentration. Specifically, 1 over m sub I. Percent or extent of ionization is directly proportional to 1 over m sub I. It's inversely proportional to m sub I. Because the greater the concentration, the smaller is the ionization extent, with no other factors being considered.
Why didn't you consider the hydronium and the acetate that was formed
For what?
for the ionization?
I did. You mean here?
Yes, sir.
Well, here's the definition. We put in the concentration of derived species, which is acetate ion. In this case, it's also hydronium ion.
So wouldn't that be squared?
No, that's not the way the percent ionization is derived. If I want to use what you're saying, I got to have a square up here. No, not defined that way. Anything else? Now, question 1824. First hinges on, I believe it's question 1820, which I told you to tackle, which was to calculate the hydronium ion concentration per thousandth molar acetic acid. If you calculate that hydronium ion concentration correctly and apply this recipe, you find out that in thousandth molar acetic acid, the ionization extent of solute acetic acid is now 13%. So you see how these two data points, here's 10th molar acetic, the ionization extent is 1.3%. Here's 1000th molar acetic, and now the ionization extent has jumped up to 13%. So this verifies the fact that ionization extent depends on the dilution factor. The less concentrated solution, the greater is the ionization extent. So, ionization extent directly proportional to 1 over m sub I. So, question 1824 goes on to say, if I deal with an acetic acid solution for which I wish to determine m sub I, and I am told that in this acetic acid solution the ionization extent of solute acetic acid is 10%, can I calculate m sub I? And before I calculate m sub I, what can I say about the molarity of this acetic acid solution relative to 1000th molar? This molarity must be greater, because the ionization extent is smaller. All right? So here's our general recipe. Because again, the only equilibrium of concern is acetic acid plus water, double arrows, hydronium ion, and acetate ion. If we are told that the ionization extent is 10%, what can we write up here for X? 0.10 mi quantity squared. Right? That's what this tells you. The ionization extent is 10% of m sub I. That means the hydronium ion concentration as well as the acetate ion concentration are each equal to 10% of m sub I. And if I write that as a decimal fraction, this is what I got. I got 2 sig figs. Well, I'm taking the 10% as 2 sig figs. Okay? What do we write in the denominator? Yup! 0.90 m sub I. Don't leave out the m sub I. You leave out the m sub I, you're saying, I know what the molarity is. That's not true. Is this hard to solve? Ha, this is a piece of cake. After you cancel m sub i's, you got m sub I to the first power. And you'll get this value. (1.6 times 10 to the minus 3 molar, the 2 sig figs, which of course we see is more concentrated than thousandth molar. All right? Another one. Question 1825 says, let's imagine we have a weak acid whose Ka value is the unusually simple value of 1.0. Let's calculate the hydronium ion concentration for 1.0 molar HAC. Now, I purposely have this question at this juncture because I want you to realize now how to wrestle with this or deal with this ionization extent business in solving problems like this. We know this, and this is again a solution of a single solute, HA. So again we can write this. Which in this case is this. Now we have recognized that if m sub I minus x is equal to or is very near to m sub I itself, we can solve this quadratic expression correctly by forgetting x in the denominator. You think you can forget x in the denominator this time? Now this solution is fairly concentrated, but look at this Ka value. Relative to the Ka values in our table for weak acids, do you see that this Ka value is a hell of a lot bigger than any of the Ka values we got in our table for weak acids? What does that suggest to you about ionization extent for HA in this solution? Substantial? Well, if it's substantial, then m sub I minus x is not going to equal m sub I. Which means to solve this, we got to keep x in the denominator. And I stated this before, I think, but I'll state it now even more emphatically. If you think I'm solving this with the quadratic formula, you're wrong. I will not use that recipe in this class, period, ever. Because it interferes with my ability to understand chemistry. Textbooks, textbook authors, teachers of chemistry have got to understand that just getting the answer is far short of what achieving education and understanding of chemistry is all about. How you get the answer is often more valuable than the answer itself. Why you want to get the answer is more valuable. And what the answer means. These are the valuable parts of the puzzle. Not filling in circles on some damn bubble sheet. That demonstrates zero understanding. Even though you may have marked the right answer. So, now that we've introduced ourselves to this percent ionization consideration, I want to show you how I'm going to apply this percent ionization consideration to crack this puzzle. I'm going to solve this by speculation on percent ionization, which I know for a weak acid or weak base, unless the acid is ionized 0% or 100%, is somewhere in between. Not a fancy statement at all. Pick me a value that's in between 0 and 100% as a test speculation for percent ionization.
50%.
I'm taking 50% first, always. Now, why do I want to take 50% first? I'll show you. You see this? If I take 50% of this as my test value, okay? 50% of this. Then what do I wind up with in the denominator? I'm taking X as being 50% of M sub I. I'm taking X to be 50% of M sub I. So for this case, it'd be 0.5, wouldn't it? That guarantees, when I try 50% ionization extent, that guarantees that the value of the denominator in this quadratic is half of M sub I. Okay? And what do you got up here? I got half of M sub I quantity squared, don't I? Which means this whole thing reduces to what? Half of M sub I. How about that? That's not too hard, is it? Here. Let's try 50%. That gives 0.50 quantity squared, because M sub I is 1.0 over 0.50. I hope you don't need this thing to solve this thing. There. So what do we recognize from this test value of 50% ionization extent? Is HA ionized to a larger extent or a smaller extent than 50%? Larger extent. Because when we got the right value for X, this term, which is this term, which is this term, is 1.0. We didn't get 1.0, we got 0.50. So what we're doing is to allow these numbers to talk to us, which is one more reason why I told you, you have to be able to speak the two parts of our language to get at this. Numbers and letters. If you keep looking at equations as mysterious, cloudy, secretive information containing things which you solve this way, you're not going to get any place with this. You let this stuff talk to you. And we've now seen a simple way by which we can let percent ionization talk to us. We haven't done anything fancy or difficult, and we now know that the true ionization extent for the hydronium ion concentration, the true ionization extent for HA in this solution exceeds 50%. So we know, without doing anything more, the hydronium ion concentration for this solution has got to be bigger than what? 0.50. Well, now with the assistance of my calculator, I'll proceed by trying additional ionization extents. Now, if you wanted to do this in what I would argue to be a systematic fashion from a rigorous arithmetic analysis standpoint, I now got percent ionization boxed between 50% and 100%. So I'd probably try 75%. And if I tried 75%, I'd have 0.75 squared divided by 0.25. And in short order fashion, I'd find that's a value bigger than 1. So I know how to play the game. Ionization extent equals 62%. How will you verify this? You'll take x squared over m sub I minus x, and you'll write in 0.62 quantity squared divided by 0.38. It's messy. Now push the button on your pocket calculator. See what this equals. What do you get?
1.012.
1.0 blah 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 blah. That's it. Done. Now I'm telling you, this method of solving, like what I showed you when we talked about solving from an algebra standpoint, the fourth order expression for the ammonia, nitrogen, hydrogen equilibrium thing. In order for this stuff to become meaningful to you, in order for this stuff to be understood by you, you have to practice it. If you refuse to practice it because it's something you haven't seen before, well then, you're not going to learn. That's wrong. We want you to learn. So we proceed. Now let's try 10,000 molar acetic acid. Now, we recognized from what we have written here that in thousandth molar acetic acid, the ionization extent of acetic acid is 13%. So whatever is the ionization extent for acetic acid in this solution has got to be bigger than 13%. And it ought to be rather substantially bigger, because this solution is 10 times more dilute than that solution. Or if you want to say it a different way, this solution is 10 times more concentrated than that solution. So we know ionization extent for acetic acid in that solution is bigger than ionization extent for acetic acid in this solution. So we start by writing our general expression of Ka, which is 1.8 times 10 to the minus 5 for acetic acid. You probably know this value by now. X squared over m sub I minus x. For this solution, do you think m sub I minus x equals or is about the same as m sub I? Hell no. I mean, for the solution that's 10 times more concentrated, you got ionization extent of 13%. Well, let's prove this. We know how to prove it. We speculate that m sub I minus x is on the order of m sub I. That means we throw away x in the denominator and see what we get for x. This gives us x max. Do you realize this gives you x max? Because anything you subtract from this makes this smaller. So when you cross multiply, you get a smaller product. And whenever you take the square root of a smaller product, you've got to get a smaller value for x. Nothing fancy about that. We're letting this damn thing talk to us. We're letting this thing tell us what does it mean. That's what you want to do. So I put in 1.0 times 10 to the minus 4. That's m sub I times Ka, after having forgotten x in the denominator. Take the square root, I get 4.2 times 10 to the minus 5. And then I realize that m sub I less 4.2 times 10 to the minus 5 is on the order of 6 times 10 to the 5th. That reduced this thing by over 40%. So I know for sure, for this solution, does this approximately equal this? Hell no. So, as with this solution, I now have another solution for which I have to solve the quadratic, and I've already told you I'm not fooling around with any quadratic recipes. And we know, because of this information, that whatever is the ionization extent for acetic acid in this solution is greater than 13%. So, to crack this puzzle, we're going to operate on this, just like in cracking this puzzle, we operated on this. And I'm going to solve this like I solved this. I'm going to solve this by speculation on ionization extent. What should I try first? 50%! What do I get if I try 50%? What do I get for the hydronium ion concentration? I'll write this over here. Operate on this. Try 50% ionization extent. Which gives me a hydronium ion concentration of what? You tell me what it is, I'll write it down. 5.0 times 10 to the minus 5. How do we know that is impossible as the correct hydronium ion concentration for this solution?
It's larger than X max.
That's larger than X max. I mean, whatever is the hydronium ion concentration for this solution, it can't be bigger than this number. So it sure as hell can't be this number, because this number is bigger than this number. Zap. Hey, let this stuff talk to us. So we now got the ionization extent in a box defined by 13% as the smallest possible ionization extent and smaller than 50%. So I'm going to write this down. (34% doesn't), which means the hydronium ion concentration is 3.4 times 10 to the minus 5. It's not hard. Now is when your pocket calculator pays handsome dividends. Once you know how to define the game, once you know the game you want to play. And we know the ionization extent is bigger than 13% and less than 50%. Well then, given that we're limited to two significant figures, we've got to be in there someplace. 40%, 50%, 60%, 70%, blah, 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 up to 49%. And our horse sense ought to tell us, whatever is the ionization extent, it's going to be substantially larger than 13% and substantially smaller than 50% because of the arithmetic we've already done. Well then, chances are, from an arithmetic analysis standpoint, with the information we've already recognized, I'd probably would try 30% next. And I'm trying 30%, I'd see that gives me a hydronium ion concentration which is a little bit smaller than the true value. That means if I put in 30% in this, and have 3.0 times 10 to the minus 5 quantity squared up here, and 7.0 times 10 to the minus 5 in the denominator, I'm going to get a value for this term which is a little bit smaller than Ka. In fact, I'll get 1.2 times 10 to the minus 5 because I've already tried the 30%. But I know I'm creeping up on it. 34% doesn't. You practice. I've showed you how to play the game. Now you play. And we go to indicators. Interesting things, indicators. You've used them in the laboratory. You will use them throughout 46 laboratory. If you want a quick, fast, reliable handle on the pH of a water solution, which is colorless, you can't beat indicator analysis. Which the one significant figure, if you do the indicator analysis correctly, will nail the pH. Let's look at this equilibrium reaction. Have you as yet in the laboratory used the indicator bromothiamol blue? Shorthand reference HBTB. If you did 45 laboratory last term or the previous term, you've used bromothiamol blue because that was part of assignment 5, part 2. Color correspondence to pH for this indicator. At pH 6.0 or lower, you see a yellow color. 7.0 on the order of pH-wise, you see a green color. 8.0 above, you see a distinct blue color. These solutions I have before you have been treated with this indicator. Now that's not a particularly shiny yellow, but it's yellow. A distinct blue. When I look at this solution and see the distinct yellow, am I looking at HBTB or am I looking at BTB minus? When I see the distinct blue, Am I looking at HBTB or am I looking at BTB minus? Or more to the point, is HBTB yellow or blue? How many vote that HBTB is yellow? If you don't vote, 4 million points off exam 1. How many vote that HBTB is blue? Most votes are dead wrong. Look at this pH information. Does this pH information not tell us as the system becomes more basic, we go from yellow to green to blue, right? It becomes more basic. That means as the hydronium ion concentration is getting smaller, as the hydroxide ion concentration is getting bigger, we go from yellow to blue. I said the same thing, just with different words. Okay? Now tell me, do you recognize that this represents an acid and this represents its conjugate base? Nothing fancy about that. And if I want to take H plus away from an acid, am I going to throw that acid into a basic solution or an acidic solution? What are you going to do to get rid of H plus from an acid? You're going to put it together with other acids or base? Base! Base is what steals protons, damn it! Like bad kids steal candy bars. So it follows as night unto day that as I make the system more basic, I'm doing a better and better job of swiping H plus from this damn thing. So this stuff is the yellow stuff. And as I take H plus from this, I convert it to a green color and then ultimately to a blue color. Now we got to let this equilibrium talk to us. Now then, with the information we have on the board, I want the approximate Ka value or the Ka value to one significant figure for the acid HBTB. The approximate Ka value. It follows from what is on the board. For this equilibrium, I'm going to write the equilibrium constant, which you know by definition corresponds to Ka for this, because it shows this acid reacting with water. And I'm going to ask a question. When you were a little kid, did you play with watercolors? Or did you just waste all your time playing with that damn computer? If I had little kids in my house today, I'll give you an hour a day with the computer, max. That's it. The rest of the time you're going to be outside playing soccer or something like that, or inside doing something which entertains the brain, like playing with watercolors. Not sitting there going, what can I find at this dumb website? Cell phone, forget that. You ain't getting that till you're 16 years old at least. I mean, you want your kids to learn? What do you want? It's up to you to decide. And it's not too far in the distant future when you folks will in fact be making these decisions. And you have to ask the question of yourself, what do I want my kid to be able to achieve? What foundations do I wish to build for my kid? Hey, I want my kid to be able to think. That's where it's all at. Think sharply and think clearly. Now again, how many played with watercolors? Wonderful! If you have a distinct yellow watercolor pigment and a distinct blue watercolor pigment, how do you make green? You mix
Equal amounts.
the yellow stuff with the blue stuff in what ratio? 1 to 1, equal amounts. And we have recognized that BTB minus is the blue stuff and HBTB is the yellow stuff. So if BTB minus is in the solution at a concentration which is equal to HBTB, which is also in the solution, and this is the blue stuff and this is the yellow stuff, and the molarities are equal, what color am I going to see? Ha ha! So when these molarities are equal and I see the green color, the hydronium ion concentration is 1 times 10 to the minus 7, which by the way is Ka. How about that? Nothing fancy about this. We're just letting this stuff talk to us. So regarding indicators, I now say to you, when you know the boundary pHs, for our HBTB stuff, the boundary pHs are 6.0 and 8.0 respectively. Because at pH 9.0, 10.0, 11.0, all we do is keep seeing blue. And at pH 5.0, 4.0, all we see is yellow. But the trip over pH, to become distinct yellow, is 6.0, and to become distinct blue is 8.0. When you have these boundary pHs for an indicator, you take the pH that's halfway between these. That's pretty easy, because pHs are logs and they relate to each other linearly. So you add the boundary pHs together, divide by 2, take the negative antilog, and guess what? You got the hydronium ion concentration as well as Ka for the indicator. That's it. Now, I'm going to jump to this demonstration since I have it here and I'd like to do it in the remaining few minutes. Then on Wednesday I will retreat to the considerations we're jumping past. I want to jump to this consideration because it relates to use and interpretation of information given to us by use of HBTB as indicator. Because these solutions, as I've already reminded you, have been prepared by using HBTB indicator. I took some from the lab. HBTB. I'm going to add a little bit more indicator to each solution just to intensify color, that's all. $200 milliliters blue solution treated with HBTB. 200 milliliters yellow solution treated with HBTB. What color will I get when I mix the solutions? That's green. Let's repeat the experiment. $200 milliliters water solution, blue, treated with HBTB. 200 milliliters yellow solution. Water's the solvent, treated with HBTB. Color? Predict. Green. Have you seen this before? Ha ha ha! Question. From what we started with, the equal volumes of the blue-yellow solutions prior to mixing, why was it not possible to predict the colorimetric outcome? Now, I want you to think about that. We'll talk about the answer to that next time. One more demonstration. Hold on. We got one more. Now, before we do this demonstration, let me tell you, at this demonstration, which we're now going to do, parallels work that you folks have done in 46 Laboratory Assignment 1 because it involves acetic acid solution. Specifically 1 molar acetic acid. I've got the shorthand reference formula HAC. Here I've collected deionized water from our white plastic knob. That's deionized water. And I want to collect an approximately equal volume of 1 molar acetic acid. That's not too bad. Now, you remember in assignment 1, 46 laboratory, using this indicator? Those of you up close, can you see the label? Methyl orange. Now I'll put the methyl orange, a bunch of drops, into the acetic acid solution, 1 molar, and methyl orange, a bunch of drops, into the deionized water. Ooh, lipstick red. Goldenrod. See, I can be inventive with these colors as well. Now comes the $64 question. Equal volumes. Goldenrod, lipstick red. What are the possible colorimetric results given that you've handled methyl orange in the laboratory? Well, the resulting solution could remain this. It could remain this. It could be red with a little bit of this color. It could be in between, which would be pretty much orange. It could be a yellow-orange. So you got 5 possibilities. Distinct this, distinct this. Red-orange, orange, yellow-orange. 5 possibilities. What is the resulting color? 5 possibilities. What is the resulting color? How many voted? The resulting color will be this. How about that? Now, why is that true? Why is that true? What the hell did we do? We took 1 molar acetic acid and we turned it into half molar acetic acid. We upped the ionization extent. We have 2 solutions of acetic acid now. 1 molar and half molar. How do the hydronium ion concentrations compare for these 2 solutions? They're very damn near about the same, aren't they? That's why this solution color is the same as what we started with the 1 molar acetic acid. Let the stuff you have talk to you. Think about it, and then you'll get there. We'll talk more about this one next time.